So since Monday, technically everybody can come every day, I guess. I'm probably putting stuff online is going to be the last of my worries. Will it get online? Yes. Will it be as detailed? Maybe, maybe not. Will it be immediately after third period like I usually try to? Probably not at all. So if y'all can come and you're deciding to stay at home, it's not my priority to rush things for you to get it. I'll probably still record live, but I'm just not gonna, like right now I try my best to have it up by the beginning of your class, which I won't today. But I probably will not try to do that anymore. Which most of y'all don't watch it then anyway. All right, so let's look at what we have in our calculator. We've got zeros in list 1 because those are our explanatory variables, which means we think it explains the change in semester 1 grades. So that's our response variables. So right now list 1 is zeros, list 2 is S1 grades. Like I said, I'm going to kind of be talking all over the place today because I want to make connections. And I don't want you to write down anything that I write unless I tell you to write it. If I am going to actually go through time to find all this out, from my perspective, what do you think I'm trying to prove about grades, zeros and grades? And what kind of correlation? As your number of zeros increases, what do you think is going to happen to your grades? So what kind of relationship is that? So this is generically our idea for what we're doing for today. You with me? Now, I won't write on an AP exam, I'm not going to write, hey, this is what I'm trying to prove. How would I end up actually writing? I would write a what and a what. I'm trying to prove something. No, I'm not trying to have hypothesis. So we're going to get to there. We would write it that way, but we're going to kind of talk through it. So let's think about where we are right now. We've got everything in our calculator. I want to see what it looks like. So what am I going to do? I'm going to go ahead and graph it. So second stat plot. Let's see if anyone happens to put it in the calculator. Let's up here. So let's graph it. We've got second stat plot. Our X list, our X's are in our list 1. Our Y's are in our list 2. What do you see in that graph? Generally, what kind of relationship do you see? Negative. Now, just talking through this, negative obviously means they're going to start higher here than they are here. Now, if I'm looking for a linear relationship, does that mean I'm looking for exactly that? No. So this could be a linear relationship because in general, I can see that they're following this pattern that way. So linear relationship doesn't mean it has to be exactly on a line or anything. Does it look fairly linear with that one? Like, can you tell the path that it's taking? Now, the one I drew on the board is pretty good, but can you generally see a path? Okay, so everything looks okay right now. So let's think through yesterday's stuff we did in the calculator. So in our list 1 right now, and you don't have to write this, this is just me talking through like I did yesterday. Right now in our list 1 is what? Our X's. What is right now in our list 2? Are our Y's observed, predicted, or neither? All right, so what do I end up wanting in list 3? All right, so now I got to figure out what to do at that point. So I need my predicted there. So where do I go in my calculator to find predicted? All right, so let's go to stat. And then where from stat? Calc. And then down to which one? Stat calc 8. So our equation, and you're plugging in x is your list 1, y is your list 2. So remember our equation starts with y hat. What does the hat stand for again? Predicted. So we end up getting an equation of y hat equals what?
85, 29, 4, 4, 9.
Stat. So stat, count, I'm going to stat. Second stat, no, stat, count, 8. And then what, 449?
No, 4, 4, 9.
And then, so that is our what? Our y-intercept. What, I did not talk about this one in class yesterday, but I didn't think that would be an issue. What does that mean to be a y-intercept? When x is 0. So in this problem, if someone were to have no zeros in all of semester 1, we would predict their semester 1 grade to be about 85.9449. I like using an actual example because it makes it easier to like see the connections and stuff like that than me just like coming up with this fake example about data that you don't care about anyway. So it kind of helps to see it that way. So the rest of my equation, minus or plus, which means my slope is negative. What is the slope?
0.7.
1 what?
7.
And then x. So that's my equation. So that's what I'm plugging in right here. When I'm highlighted here, I start with the 85.9449 minus 0.7917. And what do I plug in as x? Where are my x's? So I plug in all of that in list 1. So that gives me my predicted values. Well, I'm not really concerned with just my predicted values themselves. I'm using those to get to where I want to be. What do I end up wanting in list 4? And how do I get my residuals there?
Which 2 notices?
So now I've got all of my residuals. What is the next graph that we make? A residuals plot. So you're going back to a second stat plot. This time we are graphing what versus what as far as lists? L1 versus L4. Oh, actually, might still have these pulled up. Your graph should look something like this one. So when I'm looking at this goes back to chapter. I didn't talk anything about what we're looking for in this yesterday, right? I don't think I did. Okay, so all the way back to chapter 3, there end up being 2 things that I look for here. What do I not want to see in my residuals plot? And I realize we're on chapter 12. This is all the way back in chapter 3, so like it's a long way away. Okay, so those are the 2 things. We don't want to see a pattern, and we want to see equally scattered above and below. So we wouldn't want to see something like a trend like this, because that means what we have is not good. That means our line is not linear. But we don't see a pattern, so that's good. The other thing is equally scattered above and below 0 for all values of x. It's hard to kind of show this online, but the way one of my professors explained it, which I thought was better than just explaining that, is if I held, well, it's your fingers, but if I held this here to here and moved throughout the graph, does the distance my hands are apart really change throughout? No, not really. And that's what it means by equally scattered above and below 0 for all values of x. Technically, what we're looking for there is we don't want something that looks tremendously like this. Now, does that one start to look kind of close to it? A little bit. But if I just take that one dot out, does it look like it at all? Not really. So we want something that we don't see a distinct pattern. Equally scattered above and below zero for all values of x is kind of the way you guys would think of a pattern anyway. So those are the two things we look for there. Now we're going to go one step further and make sure that our residuals themselves are quote unquote good. So where are our residuals right now? Calculator. List 4. We want to make a histogram of our residuals. So we're going back up to a second stat plot. You don't want to do it in a second plot because then it's going to try to graph on top of each other. So just keep your plot 1. We're changing it from a scatter plot to a histogram. L2 minus L3. And so I'm doing a histogram of list 4, and we end up getting a graph that looks like this. Well, what can you tell me about that graph? So that's probably what we were looking for there. Now, I actually apparently did not do this one before the class started, and I thought it was going to end up a little bit rough. That's probably about as good as I'm ever going to get it, even if I made up a problem myself. So what we're looking for there, we want the residuals to be fairly normal for this to be a good fit line. Does that look pretty normal? Yeah. Think back to when we did a histogram before. So when we did a histogram previously in our steps, we made a histogram of what? Values. And that's why I was really picky about, like, I need the label to be a histogram of values. And at that point, it's probably like, why would I write histogram of values? Of course, it's the values. What is this one the histogram of? Residuals. And that's why I was picky before about saying that it's histogram of values, because it wasn't a histogram of residuals. What are the two things that we check for every histogram? We want to make sure that there is no strong skew and no extreme outliers. Okay, so let's go ahead and switch gears there. I am going to skip to going straight into the middle of a 4-step without actually talking about the 4-step, because there's no reason for us to write down all the conditions and then turn around and write them down on a different piece of paper. So we're just going to start just in that middle section. Now, one thing I forgot to do during third, Aaron, you might need to remind me this tomorrow. I forgot to write method. So in plan, write method, but then we're not going to talk about it right now, and then we're going to write something underneath it. So in plan, right, the method's going to be our first thing, just like always, and then we're just going to skip over that right now and go straight to our conditions. We want to see that there is a what kind of relationship between our two variables? What? Linear. Now, I'm pretty sure I came up with this, and this one wasn't in the book, because why it's so weird. This is where it gets a little funny. This is just to help us remember what these are. Well, what do you think L is going to stand for?
Linear.
Linear. What do you think I stand for when we're taking conditions? Independent. What does N stand for? Normal. Skip this one right now. What does R stand for? Random. So the only thing that shouldn't jump out at you is this one. So it starts with an E, and then slowly after that there's an A. What did we check for here? The what? Equally above and below. That's our, what's going here. So, checking our conditions, we're starting with L, which is linear. And now I know I have L here and I write linear again. I don't care if you write straight in the IN. Yeah. Now, do you really need this A over here? No, it's still weird writing liner. So I don't care if you write A like that. It just kind of helps to remember. So there are two things that we are looking for to see if our data is linear. What's the very first most obvious thing we're checking to see if it's linear? Which one? And how do we check it? We literally just, yes. When I have it in front of me, how do I check to see if it's linear? Literally just look at it. And again, we're not looking for a perfect line there, but we can kind of see that pattern that it's taking that straight line relationship. What is the second graph that we made? Alright, so we said we checked for two things in the residual plot. We just said that this part right here is checking that they are what? Equally above and below 0 for all values x. So what's the other thing we check for in a residual plot?
No pattern.
So both of those two things together, like sometimes the linear relationship visually in the scatter plot isn't going to be like super obvious, but then the residual plot, remember, is like the sideways zoomed in version, so that just kind of confirms it. So it's those two together that are going to tell us, okay, we're going in the right direction, that's linear. Just that I is what? Which is 10% condition. That's the same we've always done. There's something else with replacement also means independent, and I might come back in and write that one later, but I don't want to write it right now. What does N stand for? Normal.
We said that there are these.
Oh, yes, you can go ahead, yes. She was asking, should we still write there at least? Yes, if you want to write that there. So I'm kind of taking for granted you all good with that. Which of our graphs are we checking for normal? What are the two things we check in histogram residuals? So the no strong skew, no extreme outliers.
Do we draw a histogram or can we just look at it?
No, you'll draw it. So how many graphs do you need to draw for each one of these problems? 3. If you see one of these on the AP exam, which you probably will in some form, a lot of times what they do is make everything for you and then say, okay, now you do it. So like they'll give you all 3 graphs and like the output data, and then you have to like look at the output data to see what the equation is and all that stuff from there. So I don't think I've ever seen, I would not expect an AP exam question to make you make all graphs. But in class, obviously, I'm going to make you make one because you, like, sometimes they'll give you 2 and make you make the third one and stuff like that. Now, what do we usually write after we do this? So we can use an approximation. Now, don't write that. Making sure you understand connections because you're really good at going piece by piece and then not making connections. What is the actual reason we say so we can use normal approximation? So that I can then do what? Theoretically looking at a piece of paper. So now I can then use what? What piece of paper? The Z table, the green sheet. Now, usually we do it in our calculator and that's fine, but that's why we do it there. Now, we're not going to use the green sheet here. So we check that in the process that this one isn't extremely non-normal, but we don't need to write that there because of that. So here, now generally you guys have told me what this is, but we need to get wording specific. Equal variance. So varies equally. Now, which graph am I talking about? So the residuals plot varies equally. The end part is where people don't always remember the details. You guys are pretty good at telling me the beginning of it. It varies equally what? And now I say above and below zero, but what's the same thing as zero is the same thing as saying what? Least square regression line or x-axis. So if you say one of those, that's fine too. Varies equally above and below zero for. Do I just want it at one little spot? So all values of x, because that means all the way from left to right. That was when I did the thing where I did this back and forth all the way up and down it. That's what it means for all values of x. And then what's R stand for? Random. We're checking to see if it's what or what. Random what or random what? Alright, so now I'm gonna start to tie in and make connections for you to see what's what. You don't need to write any of this. When I'm dealing with me, what is my symbol for statistic mean? Parameter. For standard deviation, it's and right here. If I said write this equation with letters and a set of numbers, you would write y hat equals what? And then because it. So slope is what letter? Is that my statistic or parameter? What kind of values are these versus these? What kind of are these? What kind of Greek letters? What are these? Not Greek letters. English, whatever. So we need a Greek letter. We're not talking about this. What do you think is going to be the closest Greek letter to B? So that is our symbol for slope for parameter. This is kind of making connections. So like, yes, we're going to use this, but I don't need you to write that anywhere yet. You don't have to yet. We're going to write it all, but I want y'all to see connections like this. When I teach it the first time, I can tell you, I actually did tell you this, but y'all don't listen because you don't have enough information at that point. So now I'm trying to like connect everything with it. So give me my equation for this. Very, very basic, very first thing we start with. What's the other thing? X minus over, in general, some type of standard deviation. So anytime we're doing a test, we're in general using this format. If I were writing this for this test, less than, greater than, not equal to, what's going to go right here? So whatever I wrote here is going to be what goes there, right? So let's go back to where we first started with today. What am I trying to test by giving you this information? Which is where we started. That the relationship is what? More specific. This example specifically, negative. So this is a parameter. So what parameter do you think we're going to use here? So we are trying to test to see if there's information or evidence that it is a negative slope, specifically for this one. So what would I put here? So what do you think our null hypothesis claim is going to be? And technically it's one of those where opposite of that is technically greater than, but your claim is 0, which means that would look like a graph where there is no rhyme or reason to anything that's going on at all. So this means absolutely no relationship. Our options here, just like always, less than, greater than, or not equal to. So there is a relationship, there's a negative relationship, or there's a positive relationship. This is one thing that I did not talk about yet in third period. This is my values. What is my degrees of freedom for that problem? Because there were 3 categories. 3 minus 1 gave me 2. Those are all numbers. What is my degrees of freedom here? So this one was 3 minus 1. This one I found by doing everybody with me? Alright, so these I have how many variables? 1 variable, but I have 3 categories. Here, how many variables do I have? And then I have 2 categories for each. So what do you think this talks about based off of what you just told me? I only subtracted 1 because there was only 1 variable. This separate category here has a variable. This separate category here has a variable. Minus 1, minus 1. Today, we have 2 different variables, but it's all of the same data. Like, we're taking it of different individuals. So we're not doing like a 2-way table takes this variable versus this variable, right? Now we're just saying, okay, well, I want a list of the different ones. So we're not taking do I care about how many different categories of the semester 1 grade there are? No, I just care about semester 1 grade. I've got zeros. How many variables are we dealing with? I'm not sure when I said that. Look at it. How many variables are we dealing with? 2. So here we subtracted 1 because there's 1 variable. Here subtracted 1 from this variable, 1 from this variable. But we had to look at variables separate because we cared about how many were in each one. How many? Let's go to t. For a t, if our n is 15, what was our degrees of freedom? Why? Because we had how many variables? 1. So now in this one, how many are in that problem?
30.
How many variables are there?
30.
So what do you think I'm going to do? And that's why we subtract 2 instead of subtracting 1. Now, that's more detail than I usually go into with the class because people usually just remember, okay, this one's 2 instead of the other one being 1. But understanding where that comes from, I think, helps you remember which one's which. So degrees of freedom for all of this chapter is going to be n minus 2. Let's go ahead and start. Go back to state now. I'm going to start working on the core stuff. Now, you can pretty much do an entire problem. Come back to here. Okay, so here, with my test statistic, what's going to go here instead? Beta, is the same thing that fell here. This is my value for my problem. What do you think is going to go here? Because that's my value of what I'm dealing with from the problem. So the only thing we haven't talked about is some kind of standard deviation in relation to slope. Other than that, you can do this entire problem by yourselves, pretty much without me ever going over it. Alright, so starting at state, we're gonna have a null alternative hypothesis, but don't write it yet because we need something above it. So our null in general is gonna be what? Well, we can pretty much always write what this is. Now, just like with our difference chapter, I could technically put a number here and test to see if my slope is like less than, greater than, or not equal to that specific number. But that would be a very specific example and not something that we would have to do in this class. So our alternative, am I definitely going to write beta? For our class, am I definitely going to write 0? And then so my options are the same options we've had all along. So what do we always do in general before we write this stuff? So I'm going to define my population and parameter. And then now you can write it with me. So we're going to define our population in context, and then underneath that, I'm going to write what? Well, what's my first word going to be? What is this? A what? And I might come back in and write stuff there, so you might just want to leave just slope and then leave it blank for right now. Once we do a problem, you might choose to go back and write that a little bit more specific, or just write slope dot or something. What else? One tiny thing? Well, yeah, I'm probably going to come back and make our let beta part a little bit more specific when we get into problems. Just so that we can go ahead and have this written and not necessarily talk about it yet. In do, what's something that you know we're going to have in do from the problem? You said what else? There's one other thing that we may or may not have. What's the thing that I said that's missing? Standard deviation, which is written as, what do you think that stands for? Standard error, and it's subscript B, so standard error of my slope. There are times where we don't have to have that written, but I still want to write it there. So now, what is my test statistic equation?
P minus beta divided by standard error.
And then we're going to draw, shade, do all that stuff. So that's a good place to stop with that one for right now on that slide. Now, we can actually do all of this for the problem that we already have in our calculator. Because we are trying to run a what? There are two processes we take for the last 5 chapters. We're either going to run a what or a what? Test or an interval. So we're going to do this one as a test. So where do I go in my calculator? Stat test Well, look and see if you find something that looks like it would be helpful. Because it says what? LinReg, linear regression. Well, I'm dealing with linear regression. I'm not dealing with any of that other stuff. My two options are it's either a what or a what. Test or an interval, or we're doing test or an interval. Test today. So you're going to F and clicking on it. Your options are X list. Where's our X list? List 1, where's our Y list? List 2, frequency we don't ever change. That next part is written kind of funny, but it's basically just saying, what is your hypothesis? Our hypothesis is what? Less than. And then the reg equation, you can end up storing it somewhere. We're not doing anything with that, so you just don't put anything there. So list 1, list 2, frequency stays at 1, we're less than 0, and hit calculate, and you should come up with this. Now it gives us, it says T, what is that? Our test statistic, with this part. It says P, which is our what? P value. It says DF, well, that should make sense because we said degrees of freedom is n minus 2. What is A? Y-intercept. What is B? Slope. S is one thing that we have not talked about yet. We know what R squared is and we know what R is. So it gives us everything in that one test equation. So if you have to make a graph, you had to go through everything we went through. If I didn't make you graph it and just said, give me the p-value, would you have needed to do this whole part? No, because it gives you all the information for the regression equation by just doing list 1, list 2 in the test in calc. With me? Yes? So depending on what it asks for, it might not be necessary to go and do this whole part before you actually figure out what the equation is in test. Notes wise, no, I don't want to. So we need to talk about what the answer is. So today, I have a p-value of 2.56 something to the -5th. Big or small p-value? Small p-value, which means we are going to do what? Reject. What are we rejecting? And in words, what is this telling me? There's no linear relationship between the two variables because alpha is less than, or p-value is less than alpha, which means we do have evidence that what? What does this mean? There's a negative linear relationship between our two variables for our given population. Questions?